Design and validation of novel transmit beam shaping technique for distributed phased array radars. Abstract 3D surveillance radar with distributed phased array architecture requires different TX and RX beams to meet the radar's vertical coverage requirement. In typical distributed array of mxn elements, elements are arranged into m number of rows with each row having n elements, and each row of n elements are fed with a single high-power transmitter module through RF power division network. While it is advantageous to have multiple narrow beams and receive to do elevation coverage, it is better to have a single wide beam in transmit due to azimuth scan timing constraints. In such type of applications, the efficient beam forming technique can be used for same antenna to create broader beam on transmit and narrow switchable beams on receive without increasing the complexity and RF distribution losses. In this paper, the application of one of the phase-only techniques, quadratic phase weighting technique, is validated for a phased array antenna used in L-band surveillance radars. This paper brings out the comparison between results of MATLAB modeled algorithm with M simulation of hardware implemented in CST. This result gives insights of implementation aspects of phase-only technique for TX beam spoiling. Keywords: phased array antenna, beam width, beam forming, radar, MATLAB, CST, gain, phase, T/R module. Introduction. Semi-active phased array antenna with distributed array architecture is quite popular for air/surface surveillance radar applications. Unlike fully active phased array antenna, wherein each antenna element is fed by a separate T/R module, group of elements in a semi-active distributed array are fed with common RF input/output through power distribution networks. This architecture gives advantage in terms of cost due to reduced transmit/receive hardware. But, the challenge lies in designing RF distribution networks with required amplitude and phase weights to form desired beams in azimuth and elevation. In general, the azimuth beam width, AZ_BW, of antenna array for rotating radar is fixed constant, tip, 20 to 50. Taylor or Chebyshev distributions are popularly used to give amplitude weights for elements in row to generate required AZ_BW and side lobe levels, SLL. 1. The value of AZ_BW is kept same irrespective of transmit/receive mode. Fig.1 illustrates the two possible beam forming techniques to meet vertical coverage requirement on transmit. Height range: multiple TX beams, Broaden Tx Beam. Fig.1. Transmit beams, narrow and broadened. The typical natural elevation beam width of antenna array is in the range of 20 to 30. In general, 3D radar for air surveillance is expected to scan about 20 to 450 in elevation. For example, to SCAN 200 in elevation, narrow beam of 20 HAS to be switched 10 times. For AZ_BW of 20 to 50, the dwell time available at 12 RPM is in the range of 26 to 70 millisecond. A very little time of 1.3 to 3.5 millisecond is available to switch multiple high-power narrow beams to meet the required vertical coverage. Considering the scanning and switching time constraints, it is advantageous to have broadened beam on transmit rather than multiple switchable beams. On receive, multiple beams can be formed using either analog or digital beam forming based on system requirement. 2. Beam shaping approach for 16x16 phased array antenna. Consider a 16x16 phased array antenna arranged in rectangular fashion with 16 elements per row and 16 of such rows placed one over other in vertical direction. Each row has equally spaced 16 elements with each element fed with one 16 power divider, power combiner on receive, and element amplitude is tapered/weighted as per Taylor distribution, n equals 16, SLL 30 dB, NBAR 5, but all the elements are in same phase as other. This gives us a narrow beam in azimuth with side lobe level of 30 dB. As shown in Fig.2, each single row of 16 elements is fed with a T/R module which can further control the common amplitude and phase applied to the entire row. As shown in Fig.3, 16 of such rows with T/R module are stacked vertically to form the complete 16x16 array. Now we have 16 T/R modules whose transmit and receive amplitudes and phases can be controlled to achieve desired beam shape and elevation. There are different amplitude and phase distribution methods which we can use for beam shaping. The most common techniques are amplitude and phase tapering. In the distributed array radar where there is one transmitter per row, the transmitter is always driven near to saturation. Hence, any extra loss in amplitude tapering cannot be compensated at low power. Even, high power attenuators at power amplifier output are not a viable solution. So, phase-only beam shaping techniques will solve the problem of beam broadening in distributed array. However, selection of right beam shaping technique depends on transmission line technology used, waveguide/streetline/microstrip/ etc., ease of design, implementation cost, and complexity constraints. 3. Effect of phase-only excitation weighting on array factor. For a linear array of n elements spaced apart by a distance d, array factor, AF, is given as an equals amplitude excitation of nth element equals phase excitation of nth element. For phase-only weighting, n can be made equal to unity. The revised array factor can be written as the phase of each element depends on two factors. First one is the phase excitation applied to each element, and the second factor is the natural phase difference seen by each element with respect to other element due to path length and looking angle difference quantified by 2. The phase excitation weights to each element can control the vector phasor sum, resulting in constructive or destructive pattern in space. Similarly, we can synthesize an antenna radiation pattern with required beam width by calculating individual element phase excitation weights. For application of quadratic phase distribution in elevation for 16x16 array. There are many phase-only beam shaping techniques available in literature. In this paper, quadratic phase weighting method is considered and applied to the 16x16 array configuration to generate the phase weights for each row of 16 elements. The theory and detailed analysis of the method used is elaborated elsewhere. 3. Let each row of 16 elements is separated from other row by distance d, which is fixed based on frequency of operation, maximum array size limitation and gain beam width requirements. Length of the array, L, along the elevation direction is given by. For a symmetric array of even number of elements, the center two elements have same amplitude and phasor weights. Let is the maximum phase applied at the two extreme end elements of array, element 1 and 16, then the phase excitation at each element of array can be calculated as where equals coordinate of nth element along the antenna array length L. These phase excitation are also explained as phase errors. 4.Fig.4 shows the quadratic curves of n equals 16 element array for different max values, with each sample value representing particular element excitation phase. /Sarath work /miscellaneous /research paper pub 2021-22 results for paper /phi values simulation for phi maximum PNG. Fig.4, element phase excitation for n equals 16 elements for various values. VMATLAB simulation of 16x16 phased array antenna with AZ and L weights. MATLAB simulation is done to generate azimuth and elevation radiation patterns for 16x16 antenna array with isotropic elements 5. Simulation is done at L band with n equals 16 elements. Taylor distribution, n equals 16, SLL 30 dB and n bar equals 5, is used to amplitude weigh elements in azimuth. Values, 0.1, 0.2, 16, generated as per quadratic phase weighting method for various 00, 900, 1350, 180 and 2250, are given as phasor weights for 16 rows in elevation. Table I shows the phase excitation weights calculated for equals 1800 cases per equation. 3. Fig.5 shows that azimuth radiation pattern of 16x16 array for various values. It is observed that maximum directivity of array 4 equals 00 is around 28.14 dB. With azimuth beam width of 4.50, equals 00 case corresponding to the state where all the elements of array are in phase and corresponds to maximum directivity. 4, equals 1800, directivity at peak is found to be 22.83 dB. It is to be noted that the directivity is decreasing as is increasing towards 2250 from 00. But azimuth beam width remains constant at 4.50 as phase weighting and elevation do not affect the beam width in azimuth. Fig.5. Azimuth pattern of 16x16 array simulated in MATLAB with Taylor weights in azimuth and quadratic phase weights in elevation for different values. Fig.6. Elevation pattern of 16x16 array simulated in MATLAB with Taylor weights in azimuth and quadratic phase weights in elevation for different values. Fig.6 is of interest, which shows the effects of on elevation pattern as increases, directivity decreases, and the beam width flares up and increases. The energy in main beam direction is distributed to side lobes, causing side lobes to increase slightly. Directivity has reduced from 28.14 d by 4, equals 00 to 22.83 d by n, equals 1800 case. Interestingly, the beam width has increased from 4.50 to 19.20. It can also be found that pattern ripples are observed for, equals 1800 and, equals 2250. Typically, pattern variation of plus or minus 0.3 dB is observed for, equals 1800 case. Generally, pattern variation of plus or minus 1 dB is accounted in radar's link budget. So, selection of optimal for beam broadening depends on gain BW requirements and tolerance to ripple. 6. Validation of MATLAB results with CST simulation results. For validation of the proposed method, M simulation has been carried out in CST6416x16 array as configured in MATLAB for two cases, equals 00 and equals 1800. Design inputs for CST simulation are same as given for MATLAB, including Taylor weights and phase weights, except a microstrip-based folded dipole, gain of 4.8 dB, BWAZ x BWEL equals 750 x 1250, is used as antenna element for simulation purpose. 4, equals 00, Fig.11 is MATLAB simulated 3D pattern. Due to Taylor weighting in azimuth, side lobe levels are very less as compared to elevation side lobe levels, and Fig.12 shows the CST simulated 3D pattern. 4, equals 1800, Fig.13 is a MATLAB simulated 3D pattern. Beam broadening in elevation is visible as expected. Fig.14 is a CST simulated 3D pattern for the same case. For both the cases, it is established that CST pattern follows the MATLAB generated pattern. While azimuth side lobe level difference between beam peak and side lobes is observed almost same, elevation side lobe levels are degraded by 0.2-0.3 dB in CST simulation. Also, there is around 2 dB degradation of side lobe levels in equals 1800 case as compared to max equals 00 case. But this 2 dB degradation at beam width of 19.20 would not affect the detection or processing performance as much as the 2 dB degradation in SLL if the main beam width is narrow. Interestingly, 5.42 dB loss in beam peak gain is observed in CST simulation as shown in table 3.4, equals 1800 with respect to equals 00 case. Though it looks like a many-fold reduction in gain, the actual effect on ranges will not be very large and will be compensated by thoughtful waveform planning and timing. Finally, a ripple of plus or minus 0.4 dB is observed for max equals 1800 case, which can be comfortably factored under beam shape loss in radar link budget. 7. Conclusion. A 16x16 rectangular array at L-band is considered for application and analysis of phase-only beam broadening technique to widen the radar transmit beam in elevation. Quadratic phase weighting method is applied for n equals 16 elements in elevation, and corresponding radiation patterns for different cases of max, 0, 90, 135, 180 and 2250, are generated using MATLAB. For validation of MATLAB generated results, two cases, max equals 00 and max equals 1800, are considered for M simulation in CST software. All the antenna array inputs are kept constant for CST simulation except that a folded dipole antenna is used as antenna element in CST. It has been validated that by changing the phase excitations of individual elements in row by using phase-only technique of quadratic phase weighting, elevation beam width of 16x16 array has been broadened from 5.60 to 19.20. A very good agreement of results is observed between MATLAB and CST simulations results. This gives good confidence in going towards implementation and fabrication of 16x16 array for L-band surveillance radar applications, where single antenna to be used to generate single wide beam in transmit and multiple narrow switchable beams on receive by only changing the phase excitation provided to each row of 16 elements. 8. Acknowledgements. The authors would like to thank GMNS2, Shri. Umesh KS, A.G.MSMT Hirani.B and DGM Shri. Muralira.NF for their continuous support and guidance in publishing this research work.